Hi, sorry I couldn't be with you today, but thought we'd try this video method for doing the lecture. And I want to try and get through the lecture pretty quickly so that you can have at least half an hour for working on the in-class exercise today. So the in-class exercise today actually has you modify the Hello World project. You'll use some of the standard I/O routines that we'll talk about in the lecture today. Compile that project, copy it over to the virtual machine, and then run it. Going through all the steps to build an RTEMS application, and then so once we're over that hurdle, we can actually start building our own RTEMS applications next time. Homework 1 is due, so make sure you hand that in. Homework 2 is already posted on the course website. And you should have the lecture notes in hand. And then, so today I want to talk about some topics from the textbook on developing for embedded systems. And then we'll cover the standard IOC file streams because you will be using those for IO here over the next couple of applications, RTEMS applications. So I wanted to review those. So let's see. So, as you're aware, developing for embedded systems is a little bit different than developing for applications for your own PC. Development is done on a host system. For a target system, you have to use a cross-compiler, or so the process is known as cross-platform development. So you use a cross-compiler on the host that produces executables that run on the target. Of course, you do need some way to target, to actually transfer the application from the host machine to the target. This slide actually shows you can do that either via serial or Ethernet or JTAG, or USB connection is common now. So you have to have a cross-compiler, a linker, source-level debugger, all running on the host system. That's designed to produce machine code for the target processor. On the target, you have to have typically some sort of embedded loader to actually start up your application once you power it on. So these go by different names or have different capabilities: a dynamic loader, link loader, monitor, or debug agent. Okay. So to develop for an embedded system typically requires a lot more knowledge of the target architecture and the compile and link process than development for a general purpose OS. So how do we transfer the image? How is the image loaded at runtime? How do we debug the program? Again, those tend to vary a little bit as you move from one target platform to another target platform. So again, on the host system, we've got a compiler that produces object files. We typically will use make and make files to control that compilation and linking process. And then there's a linker, a second program that takes all of our .o files and produces a single executable image that we then transfer to the target platform. Okay, so a number of different tools are involved. I know this slide's a little hard to read. It's a copy of a page out of the textbook, so it's going to be a little clearer in the textbook. But we have C, C++ source and header files. We could have assembly files. There could be a linker command script that controls where all of the code gets located in memory. A make file, so compile, assemble, pre-process, all controlled by make, all to produce different object files. And then we have a linker that will take our object files in addition to library files to produce our final executable image file that we transfer to the target. So object files and executable files are not just pure machine code. Each file has a particular format. We'll see that what RTEMS uses is a particular format known as the ELF format, ELF, which is also used by Linux. But again, Linux files won't run on our RTEMS machine, and our RTEMS applications won't run on Linux. they are ELF compatible files, but they have different layouts because they're for different architectures. I think the PC, the Windows uses a particular file format called the COFF format, COFF. Again, these are standard formats that tell that indicate how the executable or object file should be laid out. So each object file, when we compile these to create our .o files, not really clear where these .o files are going to be located in physical memory. Eventually, everything has to be assigned a true address on the target processor. But when we create the O files, what's in each object file are both a symbol table and a relocation table. The symbol table maps variable and function names to their relative address locations relative to the start of the code in the .o file. And then the relocation table contains a list to all references in the file. So the layout's a little bit like this. So in this particular case, there's a foobar variable that's at address 80 relative to the beginning of the file. Now, when this gets loaded into actual memory on the target processor, that variable is not going to be at location 80. I don't know actually where it will be. It depends on where the linker actually puts it a little later on. But wherever it is, the rest of the code may have references to foobar. There may be a line in your code like showing here that foobar is equal to 10. Well, this particular line of code or this particular address to foobar is at location 100, offset 100 in our binary code. So when this actually gets loaded on the target processor, what the linker has to resolve is that what the actual address of foobar is, and it'll still be offset at 80 relative to the start of this code. But then the linker has to go into process the .o file, look for all references to foobar, and then replace that reference address with the actual address of the foobar variable. And it has to do that not only for variables but also function references as well. So the linker uses those two tables, and then something that's known as a linker script to assign true addresses to all of the variables and all of the functions. So when the linker resolves all of that and creates an executable image where all the references are resolved. I should point out that actually on a general purpose operating system like Windows or Linux, there's a third piece of software called the loader that loads your program into some available memory space, and that the loader may actually do additional memory location fix-ups. But on a embedded system, a loader is typically not used, and so the linker is responsible for determining the final address of all functions and variables. So again, RTEMS, I've already mentioned this, uses a particular file format known as ELF for executable and linking format. But the binary instructions, the data, the symbol table, the relocation table, and debug information are all contained in different sections of that file. There's a handy command called readelf. Now we want to use the RTEMS version, so it's i386 RTEMS readelf. That will actually take our RTEMS executable, the one we produced last time, hello.exe. You can run that on our hello.exe. You have to run this command from the same directory that contains hello.exe, and it'll print out a long list of information about the different sizes of the different sections of the ELF file, give you some information about the particular type of ELF file, the way the data is stored in the file. We'll talk about these different sections later on. The text section is actually the section that contains our machine code. The data section contains initialized data, and then the BSS section contains data space for variables that are not initialized. It's actually initialized to 0. But we'll look at those a little later on. So sections of the image have to be mapped to particular areas of memory using what's known as a linker script. So fortunately, because we're developing for a well-known platform, the PC, we don't have to write our own linker script. But if you have to port an operating system to a new processor, you would have to develop your own linker script. So here's showing that any particular target platform, in certain areas of memory, you're going to have RAM, perhaps flash, perhaps ROM available at different addresses, different fixed addresses, and the linker needs to be aware of where these different types of memory are located, so it knows to load only changeable variables or writable variables into RAM, for example. The particular linker we're using is called LD. Of course, for our RTIMs, it's i386 RTIMs LD. And again, since we're developing for the PC, we don't have to write any special linker scripts. Okay. I want to go on to something completely new now. I talk about coverage of C file streams here. So primarily because they used to in CS210 teach C++ and cover IO stream classes, and so students got to this course and had never encountered the standard IO streams before. It's my understanding now they teach C-style IO and CS210 and program in C. So you've seen this before, but I'll just review it quickly because we'll be using these routines to do some basic IO with our RTIMs operating system. So typically, if you're going to write to a file, you call fopen. That returns a file star pointer, and then that pointer is used in all other references to that file. So here's an example where we open a file. The second argument being W indicates that we're opening it for output or write access. And then we use printf, fprintf, to print to that file. And this second argument here is a format string. It's got a format specifier %d, which indicates we're actually going to print an integer to the file. So it'll print ASCII text. The %d specifier says convert this variable from binary to its ASCII decimal representation and write that out to the file. And then finally we close the file. Okay. So in the fopen routine opens a file, and then the argument can be one of read, write, or append, or you can open with read, write, or append access to update. You get 3 streams that are automatically open for you, and these are the ones we'll be using primarily: our standard in, standard output, and standard error. By default, standard in comes from your keyboard. Standard output and standard error are both directed toward your terminal or your output monitor. Again, these can be typically redirected or referred somewhere else. We use fprintf to convert a binary number to its ASCII representation, and you have to match the format specifier to the data type. So %s is used to print char strings. These are char arrays. These arrays need to be 0 terminated, so the last element of the string has to be a binary 0. Okay, not an ASCII 0, but a binary 0 indicating the end of the C string. And then the corresponding format converter for an integer is %d. For floating point numbers, it's actually %f. We use fscanf to read data in from what's typed in at the keyboard, and this is a little trickier because what we actually have to pass, what fscanf requires as its variable arguments, are pointers to locations where that information is stored. And of course we need the pointer, not the value, because we need the address of where we want to store the data. Now strings, the name of a string is automatically its address because strings are arrays. But here, if we want to read a value from the keyboard into an integer, we need to have the corresponding format specifier, %d, and then the ampersand here is going to pass as this argument the address of age and not the value of age. Similarly, if we're reading in double values, make sure you use %lf to indicate that these are the corresponding variables here are doubles. The ampersand would pass as the argument here the address of these two doubles, and use %f for floats instead of doubles. You also have putc, putchar, fgetc for working with single characters. Sprintf is useful for printing to a char array instead of an output stream, and similarly scanf can be used to read from a char array. So scanf is a handy way to convert ASCII decimal strings to their binary representation. Okay. C file streams are buffered, so you don't normally see the output until the buffer becomes full. Okay. You can flush the output with a special routine called flush, like flush standard out would flush standard output, for example. Output is normally flushed when the buffer is full or when an input routine is called, because when you call an input routine, it's expected that normally you are trying to display a prompt before, like fscanf, where you're trying to read a number. So the flushing is usually automatic under most operating systems. It's not automatic with RTEMs though. So if you print a prompt, and you will be doing this in today's exercise, before you read in a number using fscanf, make sure you call flush standard out. Otherwise, you won't see the prompt until much later when the buffer becomes full. But you'll want to see the prompt prior to fscanf being called. It's important because of this behavior in RTEMs. When you write an application that crashes, you may not have a good idea of where the crash actually occurs. Even if you go through and sprinkle fprintf statements throughout your code, it may crash and then the buffer have information in it. When you're debugging for debugging purposes, you may want to include an flush statement after your fprint statements. It's less efficient, but it can be useful for debugging. Okay, I think that's it. Again, I promised you a short video here, so we're just well, I guess it's been about 20 minutes, but you should have a lot of time left to work on the in-class exercise today. So I will be back to class on Thursday. I'll be back actually in my office tomorrow. So if you have questions, please come and see me.